This is the screencast for section 6.4, example 6, using Newton's law of cooling. Yay, physics. All right, so if T is the temperature of the object at time little t and T sub, oh, there's so many T's. Okay, basically what we have is we have this object, the temperature of the surrounding medium, so the water maybe that it's sitting in is T sub S. The temperature of the actual object itself is T. The initial temperature of that object then would be T sub 0, and then little t is time, as stated here. Well, basically, we can say that the change in temperature is proportional to the difference between the temperature of the surrounding medium and the temperature of the object. That's what Newton came up with. Now, of course, that's going to be a negative K value because those temperatures are going to be decreasing since they are cooling. Now, we also know that the change in temperature equals the change in the difference of the temperatures of the surrounding medium and the object, which means then I can substitute T minus T sub S in for this initial differential here. And then, so since I have the derivative of the difference in temperatures equals the negative K, or proportional to those difference in temperatures, my outputs, I'm dealing with exponential. So I can say T minus T sub S, or my Y value per se, equals T sub 0 minus T sub S e to the negative KT. This is Newton's law of cooling. You do not have to have this formula memorized, but you have to know how to use it. So in example 6 here, using Newton's law of cooling, a hard-boiled egg at 98 degrees Celsius is put in a pan under running 18. Oh my gosh. Okay, wait. All these temperatures. So let's go one by one. A hard-boiled egg at 98 degrees Celsius. Well, that is going to be the temperature the egg was initially at, so the initial temperature T sub 0. It is put in a pan under running 18 degrees Celsius water to cool. Well, that's the temperature of the surrounding medium at time 0. After 5 minutes, so that's little t, the egg's temperature is found to be 38 degrees Celsius, so that's a T, regular T. How much longer will it take the egg to reach 20 degrees Celsius? So 20 degrees Celsius is our new capital T value. Well, none of this problem is talking about a rate of change, so I'm going to use Newton's law of cooling. That's this formula over here. And my T sub S is 18. My T sub 0 is 98. My T sub S again is 18. And now I need to solve for K. So I'm going to use the given information, the initial value kind of, where at time 5 seconds, the temperature of the egg was 38 degrees Celsius. So I'm going to plug that in. And now I got to solve for K. So I'm going to simplify, divide both sides by 80. Now I'm trying to find an exponent, so I got to use logs. Of course, I'm going to use log base e, so natural log of 1/4 equals negative 5k. Divide both sides by negative 5, and I can still simplify that. The natural log of 1/4 is really the natural log of 4 to the negative 1. Remember, that exponent can come out in front, and that's going to be 0.2 natural log of 4. So that's my k value. Well, now I've got Newton's law of cooling all set up. T minus 18 equals 80 e to the negative 0.2 natural log of 4t. Final question says, how much longer will it take the egg to reach 20 degrees Celsius? So 20 degrees Celsius is going to go in for my capital T, and I'm solving for lowercase t. How much time? So some more simplification. Divide both sides by 80. Change back into log form since t is in the exponent. And then divide both sides by that k value, and I get 13.305 seconds. Now that's how long it'll take the egg to reach 20 degrees Celsius. The question doesn't ask that. It says, how much longer will it take the egg to reach 20 degrees Celsius? So past those 5 seconds. So I take the 13.305 minus 5, and I get about 18.305. Oh, I kept saying seconds. It's minutes. Minutes longer than the original 5 minutes to get to the 38 degrees Celsius. Then now try problem number 31 is cooling soup. Soup. Noodle soup. Suppose that a cup of soup cooled from 90 degrees Celsius to 60 degrees Celsius in 10 minutes in a room whose temperature was 20 degrees Celsius. Use Newton's law of cooling to answer the following questions. So again, Newton's law of cooling came from his observation that the rate that an object's temperature changes at any given time is proportional to the difference between the temperature and that of the surrounding stuff that it's in, the surrounding medium. Using a negative K is the Newton's law of cooling. It really should apply to warming as well. But anyway, how much longer would it take the soup to cool to 35 degrees Celsius? So we're going to use Newton's law of cooling, and I can set up with my initial information. 20 is going to be the temperature of the air, so the surrounding medium. 90 is the initial temperature of the object, and then we've got the temperature of the air again. So now we need to solve for K, the constant here, and I'm going to use the rest of the given information that at 10 minutes it cooled to 60 degrees, so 10 in for T, 60 in for, well, 10 in for little t, 60 in for capital T. Now I'm going to solve for K. And I get that K is the natural log of 4/7 over negative 10, or negative 0.1 times the natural log of 4/7. It doesn't matter. So now I've got Newton's law of cooling all set up and ready to go, so I can find out, I've got the K value solved for, so I can find out how much longer it'll take the soup to cool to 35 degrees Celsius. That's what I'm going to put in for capital T. And now I need to solve for T in the exponent. So first I'm going to do a little simplification. And then now that I have the base E alone, I can change this to log form, divide both sides by that coefficient of T, and I get 27.527 is approximately T. That's how long it takes to cool to 35 degrees Celsius. That's not what the question is asking. How much longer? So in other words, after the 10 minutes, how much longer would it take? Well, that's going to be about 17.527 minutes more. Now part B says, instead of being left to stand in the room, the cup of 90 degrees Celsius soup is put into a freezer whose temperature is negative 15 degrees Celsius. How long will it take the soup to cool from 90 degrees to 35 degrees Celsius? So you may expect it to cool a little bit faster. Let's see. So I'll set up Newton's law of cooling, and fortunately for me, I get to use the same value as K as we did before, so I don't have to resolve for that, which is nice. We're still dealing with the same substance. And then I can plug in 35 degrees Celsius for my capital T, and then solve, and I get about 13.26 minutes from start to finish. So it saved quite a bit of time, actually. 27 minutes from start to finish in the temperature, dealing with the temperature of the room, versus 13.26 minutes in the freezer. So if you want your soup to cool fast, put it in the freezer.